general reactor, we might feed A and B. We might have a reaction where A and B go to some desired product. So the desired product comes out. This is a desired product. If we do that, we can do our degrees of freedom. And if we look at the variables, we have how many flows? I've got 2 flows in and 1 flow out is 3 flows. I've got 1 reaction, so I'd have 4 variables in this problem, 3 flow rates and 1 extent of reaction. If I look at the equations, let's see, what do I need? I might have a basis, would give me 1 reaction, one flow, and then I might have, and I've got material balances. How many material balances? 3, because I've got 3 components. There we go. So as long as I've got a basis, the whole thing is solved. Everything goes in, everything's reacted, everything comes out. So this would be my my perfect reactor. All reactions work like that. Our job figured easy. We just put in the reactants, we get out the product. That's great. If we had not a perfect reactor, but a real reactor, I'm going to feed in A and B, but I might also have a contaminant, C. I might get A and B going to some desired some desired product, so I get D out. But I might also get A reacting with that contaminant and giving me E, so I might then have E coming out, which I might not want. I might also have that product reacting away and having a further reaction and going to another product F. And that's not really what I want either. I also might not have everything react, so I might have A and B still come out and C still come out. So in a real reactor, we have a lot more species of stuff going on. Let's see, A plus B goes to D and A plus C goes to E. I call this a parallel reaction because it happens in parallel. A is doing these 2 different things. If A plus B goes to D and then D further reacts, I call this a series reaction. So what else? So E and F are byproducts. And then I have those reactants in the product stream also. Okay, so now if I do my degrees of freedom, variables, how many flows do I have? A, B, C, D, F, A, B, C. I've got 9 flows. How many reactions? 1, 2, 3. So now I've got 12 variables to keep track of. And equations, let's see, I have a basis. What I put in, so maybe there's 1. Material balances. A, B, C, D, E, and F. I've got 6 material balances. Great, so I've got at least 5 degrees of freedom left to take care of. So what do we do with our, okay, so in a real reactor, we've got extra stuff going on. We have a bunch more variables. What do we need to do? We're going to design a reactor. What do we need to have? Monday we just came back from spring break, so I'll go. So we're going to have a whole bunch of specifications. Okay, so we're we're going to have to know something about the reaction that goes on. So this might be our chemists running the reaction in a lab scale and telling us the yield is 20%, or we get this much contaminants. We're going to need additional data to come in. Or maybe we do some thermodynamic calculations to see what we think is going to come out. Okay, so we've talked about some specifications already. We've talked about fractional conversion. We had some definitions for that. So today I want to talk about yield, and I want to talk about selectivity. So basically when we have these extra reactions going on, there's extra stuff coming out. So, again, let's write A plus B goes to a desired product D. A plus B goes to some undesired product 1. Maybe with the same reactants, this would be our parallel reaction. And then A plus our product can give us a second undesired product. And this is our series. So, start with our reactants. We want them to go to products, but the reactants can go to undesired products. Instead of going to the products, and our products can also react away and go to undesired products. Want to ultimately control these pathways, maybe with catalysts, or maybe with reaction conditions, temperatures, pressures, concentrations. So we need a way to quantitatively analyze these different pathways and how much we get. Okay, so selectivity. And for selectivity, we always have to define what components we're talking about. So if we have selectivity of A going, some reactant A going to some product P. This is called fractional selectivity. We basically want to know how many moles of A are converted to the product P divided by how many moles A that are consumed. So let's see, how much gets converted to product? You remember our equations from before break? How much gets converted to products? We take our reaction, extensive reaction, and we multiply by nu sub P. That would tell me if got, say, 1,000 moles per hour being generated of the reaction, and then I multiply by the stoichiometric coefficient of P. That'll tell me how many moles of P I have that I've generated, and then I need to sum this over each reaction K if I've got multiple reactions, and the sum is over K reactions. That tells me how many moles of P I've produced. I want to know how many moles of A got converted to P, so I need to then change this into A. So I'm going to multiply by nu A over nu P. Actually, nu A1 over nu P1. I'm going to do this for reaction 1, assuming the first reaction is the one that goes to product. There may be multiple reactions that go to product, so we'll just take the ratio of the first reaction. All right, that's the number of moles of A. Don't have a minus sign in my notes, but I want to say there's a minus sign here because this is going to be negative. Yeah, okay. Let's see, divided by moles of A consumed. How much A is consumed? Well, here I can sum over the K reactions. Nu A K is I dot K. So how much A gets consumed? Oh, and that's negative also, so there's my other sign. There's my minus, which cancel this minus up here. Great. So So what I'm doing is I'm summing over all the reactions where I consume A. I'm summing over all the reactions that make P. We've got to use our extended reaction. It comes real handy. And sum over all these reactions. Okay, so yield. Yield of A that goes to P. It's also a fraction. We call this fractional yield. So fraction of yield is moles of A converted to P divided by moles of A fed. So how much we get out of how much we put into the reactor. So how much we get is the same as the numerator up here, nu A1 over nu P1, sum over K reactions, nu PK, xi dot K. So the numerator is the same, and then how much A is fed? Well, that's just Na in dot. The negative's still here because that's the nu A1 is going to be negative, and that's a positive. It doesn't cancel this time. So yes, thank you. There's a negative. There's a minus sign in the numerator there. Okay. We had talked about before fractional conversion of A. So just for completeness, you have this in your notes already, but fractional conversion is moles of A converted to P over moles of A fed is sum of nu AK psi dot. No, sorry. Moles of A consumed. So we don't care what it goes to, just how. Fractional conversion is just how much reacts. We don't care what it goes to. We're not caring about the specificity. So how much A is consumed versus how much A is fed. So this is just nu AK times xi dot K over Na in dot. Sum over K. So there's a nice relationship between these, and that's that the yield of A to P is just the fractional conversion of A times the selectivity that A goes to P. So fractional conversion is going to capture everything that reacts. Selectivity is going to tell you of the stuff that reacts, how much goes to the product. The product of those two gives you the yield. All right, any questions about these? Is the math okay? So all these have xi dot in them. This is good for continuous systems with a differential balance. Could we do it for batch systems over a time interval? thing. Let's see. So I wrote these all in terms of moles. What if I did it in terms of mass? How does it change in terms if I want to do the yield in mass or the selectivity by mass?
We need molecular weight of each component.
We need molecular weights. Which components where? Let's go ahead and just put them in. Where we want the molecular weight of which species? Moles of A converted to P. Let's change it to mass of A converted to P. So multiply by M of A, okay, and on the bottom, same formula. Mass of A on top, mass of A on the bottom. Okay, so that doesn't matter. One type of reaction that we often see in selectivity is oxidation. Oxidation can be very non-specific. You can oxidize almost anything, and you can oxidize things to different degrees. So this is ethanol, and this is in biology. Ethanol in the body gets broken down by alcohol dehydrogenase to acetaldehyde, and then acetaldehyde dehydrogenase pulls another hydrogen off and changes it to acetic acid. These are the enzymes that do that in the body. So your body controls this very specifically. Alcohol dehydrogenase can do just that reaction, and the acetaldehyde dehydrogenase can also control just that reaction. Industrially, you'll get other things happening. In biology, these are pretty important to control these when there's mutations here. These are linked to alcoholism, so mutations in these, either of these genes that change this metabolism is known to affect the way the body processes alcohol and the way people perceive it. Acetaldehyde is important industrially for manufacturing. It's also in coffee, it's in bread, it's in fruit. The buildup of acetaldehyde is thought to be one of the components of hangovers. If you have too much of that around for too long, that won't make you feel good. So industrially, here's the reactions. Basically, we're just adding oxygen. We can take ethanol, we can add oxygen, we can get acetaldehyde. We can take alcohol, we can add oxygen, and adding oxygen is what we do when we burn things. So we can do complete combustion, go all the way to carbon dioxide and water. So is this a parallel or series reaction? And then reaction 3, the acetaldehyde plus oxygen. So our product can take more oxygen and go all the way to acetic acid. Parallel or series? Series. Okay. Cool. If we call that reaction 1, reaction 2, and reaction 3, we find the fractional conversion of ethanol. Can we find the selectivity of ethanol to acetaldehyde? And can we find the yield of ethanol to acetaldehyde? So to do that, what I would recommend is, if we're doing it on a spreadsheet or a string table just to get organized, we can take each compound, say ethanol, and we can say, what is the sum of reactions times the stoichiometric coefficient of that reaction. So for ethanol, basically this is our reaction rate of component I. So for ethanol, we're consuming, in the first reaction, we're consuming 1 mole. In the second reaction, we're consuming 1 mole. These are dots, these are rates. So I've got extent to reaction 1, extent to reactions 2, minus I1 dot, minus I2 dot. So can you fill out the rest of the table? Oxygen, acetaldehyde, we've got water being produced, acetic acid, and CO2. I mean, do you have oxygen? Do you have acetaldehyde, or acetaldehyde, do you have? Cy1. Minus 2, Zy.3, water. Zy1 plus 3, Zy2. And acetic acid. 2 Zy3 dots. 2 Zy2 dots. All right, we get acetaldehyde. 2, 3. 3 Xi2. Is everything else okay? Okay. I give you exercises I like to get your brain going and to engage, because I know it's Monday morning and I know you can just listen to me. So I do want you to do these, even if they're really easy and kind of dumb. Okay, so fractional conversion of ethanol. What do we need to know for that one? The moles of ethanol consumed over moles of ethanol fed. So moles of ethanol consumed, it's right there, minus Xi1 dot, minus Xi2 dot, over moles of ethanol fed, n dot ethanol in. Feel like I'm missing a sign. I think I need a sign here. And then minus there is Xi1 dot plus Xi2 dot over n ethanol n dot. There it goes. There's fractional conversion of ethanol. Selectivity of ethanol to acetaldehyde. So now I need to know how much ethanol I consumed, but also how much acetaldehyde we generated. So I want Xi1 dot minus 2 Xi3 dot over Xi1 dot plus Xi2 dot. This one over that one, and then I've got some signs to take care of it, some stoichiometric ratios. Let's see, minus nu A1 over nu P1 is minus 1 over 1, because I take 1 ethanol and go to 1 acetaldehyde. 1 over 1. There's a minus there. So over product, so over the reactants. This minus can come down here, so I get Xi1 dot minus 2 Xi dot 3 over Xi1 dot plus Xi2 dot. Make any mistakes? Look okay? All right, and then the yield, ethanol to acetaldehyde. Why don't you guys crank that out real quick? Do you want to try again, Jim? Yeah, oh, sorry, yeah, Jay.
So if you multiply a fractional conversion in S to BC, then you get Psi1 minus 2 Psi2 over n dn.
Do we agree?
It's actually 3, but I think,
Three.
yeah, I just didn't see it because he's far away from
This one's I3?
this. Yeah.
Great. Okay, cool. Good. Okay, so we got expressions, and we can plug those into process problems. Okay, so you get the idea. So let's say we want to manufacture acetaldehyde. Let's say we want to determine all flow rates in and out of a reactor producing 1,200 kilogram moles per hour of acetaldehyde from ethanol and air. Let's say we have an ethanol oxygen feed ratio 5.7 to 1. Let's say we're told the reactor achieves 25% conversion with a selectivity of 0.6 for acetaldehyde. The only byproducts are acetic acid and water, and no oxygen is in the output stream. Where do we start? Draw a picture, specify system, 10 steps. We get a few minutes, so why don't you start plugging through and solving this problem. Ethanol, air, what comes out?
I think it was that, CH.
Yes, acetaldehyde, spell NaC.
And water
Water and acetic acid. fractional conversion, it's not 100%. Okay. Great, anything else? All right, so what do we have? So what equations do we have? What kind of specifications here? All flow rates in and out of a reactor producing 1200 kg/mole acetaldehyde. So what does that tell us? It's like our basis in our product. So what I could do, let's see, let's call this stream 1, stream 2, and stream 3. So I have N dot acetaldehyde in stream 3, 1200 kilogram moles per hour. Ethanol oxygen feed ratio 5.7 to 1. So what variables would I use for that? Feed ratio. So ethanol, N dot ethanol in stream 1 over oxygen. So N dot oxygen in stream 2. The reactor achieves 25% conversion. Need a formula for that. Let's see, here's our conversion. Psi1 dot plus Psi2 dot. Fractional conversion equals Psi1 dot plus Psi2 dot over ethanol in, and that just stream 1. Just plug things in. Let's do a DOF. Let's see. For variables, how many stream variables do we have? 1, 2, 3, 4, 5, 6, 7, 8. How many reactions? Okay, so we actually have 2 reactions. Because reaction 2 doesn't go, so we've got 10 variables. Equations. Let's see, how many flows do we have specified? Just the product stream, that's 1. How many system specs? We're given a fractional conversion, we're given a selectivity. Those are 2 system specs. How many stream specifications, stream composition specs? 1 for air and ethanol oxygen. So we actually have 2. So we've got air and we've got ethanol oxygen. We didn't write that one down. How about N dot oxygen in stream 2 over N dot nitrogen in stream 2? It is 21 over 79. And how many material balances? Ethanol, oxygen, nitrogen, acetaldehyde, water, acetic acid. I think it's 6. 6, 7, 8, 9, 10, 11. I think I counted something wrong.
Just like discount error because like that percentage is like already known, and then the problem will be specified.
So discount which?
Since like the composition of air is like known and not necessarily part of the process, you can remove that. Like
Well, I still have 2 streams though. I have two stream variables and 1 specification. Right? So I still have I still have a net 1 unknown there. I don't know. I don't know what I did. Yeah.
So, did you say you skipped the reaction? You said there were only 2 reactions?
Yeah.
Not the 3?
Yeah, there's only 2 reactions. Right? Because there's no. There we go. Those are our 2 reactions. You know, this might be a trick one because all the oxygen goes away and those 2 reactions kind of look like 1 net I don't know. I'm not sure. I don't have the DOF in my notes. I thought it would work out. I must have missed something. Yeah?
When I solved it, just kind of like using side, as if there was a side 2, just the CO2. It ended up being like, I was able to solve for side 3, and then side 2 was 800 minus 2 side 3, and side 3 was 400, so side 2 was 0.
Yeah, but you know that because you have no CO2. Yeah, okay, I'm not sure. Okay, so okay, so now I've wasted the time on the DOF. How do we solve this? We just kind of start plugging through and solving things. So I know the acetic acid flow rate. I've got Xy1, Xy3, and Xy1 related here. Well, I have to write out my material balances. I don't have Xy2. I've got Xy1 in my ethanol balance, and I've got Xy3 in the other balances. I'm not going to see it right away. Oh, there we go. We got that acetic acid production is known. That's Xy1 and Xy3. And then we have another equation for Xy1 and Xy3. So we can start there. We can solve 2 equations for those 2, and we can get those solved. We can get to extensive reaction, and then everything else is going to kind of follow through. So. All right. The point today is you have yield, and you have specificity, and you have fractional conversion. These are all ways to specify real reactors that are not perfect reactors. You should be able to calculate those quantities from the flows. You should also be able to write specifications and use those specifications effectively in problem solving.